I'm going to be talking about blockchain as a technical survey. So really, before I talk about myself, really I want to open up this space to start a discussion. You're going to have a lot of questions, I'm sure, after all the information that's been thrown at you today. So please feel free to ask questions. And we might not get through all the slides, but I'll make them available. And so you're welcome to ask me questions during the presentation, after the presentation, or follow up with an email. So about me, I'm a student at UC Berkeley studying computer science and bioengineering, and I've been in the blockchain space for about 2 years now. So when I say I've been in this space, that means I've been actively developing, contributing to open source projects, and then currently I teach the blockchain fundamentals class at UC Berkeley. So that's an open source class. We've made all of the curriculum, which we've designed ourselves, available to everybody, and we're launching an edX course. I think it's coming out this summer, but blockchain fundamentals is currently the world's only survey class meant for undergraduates, and so we have about 200 students, 160 registered, and then about 40 auditors, people who are just interested. And then I also do blockchain executive education, so a lot of companies ask us to come out to present on what blockchain is, what the use cases are, a lot like this. But yeah, so that's my background. If you have any questions, definitely ask. So today we're going to talk about block composition, Bitcoin script, and then I know you guys already talked about scalability and Lightning Network, but those are some complicated topics, and so I'll reopen up the discussion for that. And then we can end with some extra interesting things like Monero or Zcash and going over zero-knowledge proofs, for instance, but lots of interesting stuff in this space, and it's important to have context before we dive in. So let's get started. So before we go on, has anybody introduced you like the difference between Bitcoin and Ethereum? Can I get a thumbs up if yes or no? Thumbs up? We already know Ethereum, right? Okay. But the keywords I would like to point out, and I think this was mentioned earlier. So Bitcoin is a stack-based primitive scripting language, and it's not Turing complete, versus Ethereum, which is Turing complete. We're going to talk about Bitcoin because, well, we talk about Bitcoin because it's the original blockchain. And when we talk about block composition, it's useful to talk about Bitcoin because it's the simplest, and all of the others iteratively get more complicated. So today we're going to talk about Bitcoin and Bitcoin scripting language. Okay. So a tamper-evident database. This should be familiar language already by now. We have a block, and our block has a block header. It has a previous block hash. It's going to have a nonce and a MERKLE root. We're going to hash all of that together, and that's essentially what we're going to call a block. Okay, this should make sense, yes? Okay, and you guys are familiar already with what a MERKLE root is. So a block header is going to be consisting of this hash of the previous block hash, and this is what links our blockchain together, right? Because since we create that hash based off of the last previous block hash, it's necessary that it came from that last one. And because we've hashed it, because of that avalanche effect of hashes, if anything changed in that last block, we know for sure. And so in this new block that we're building, it is dependent on the last block. And then we have the MERKLE root, which is the summary of all of our transactions. And we have this nonce, this extra constant. So we explore a little bit more about the MERKLE root. This looks familiar, yes? We have all the transactions here on the bottom, and then we hash them, and then we hash them again, and we keep hashing until we have one single thing at the top. And then if we get any if we have any transaction that's tampered, it's very easily verifiable. Any questions about this? It's quite straightforward, right? Okay. So these transactions are, this transaction evolves and becomes, it will get hashed together with this second transaction, and then at the end we'll have this concatenation of all the transactions, and that's what ends up in the MERKLE root. Okay, so then we talk about the previous block hash. I'm assuming no questions, yes? This was just talked about? Okay, so we'll talk about what is composed in the previous block hash. So in the previous block hash, as I said earlier, we have the block header that feeds into the previous block hash, and this is how we get this chaining effect. And so we hash the SHA-256, we hash it twice, and this is where we have that puzzle that was spoken about earlier. This proof of work puzzle is essentially, we change this nonce so that the previous block hash, this hash that we get for the block, will fulfill some puzzle that the network has posed. So more specifically for Bitcoin, that puzzle looks like I need my resulting block hash to have some leading number of zeros. So I'm just going to brute force and change my nonce until that hash fulfills some leading number of zeros. Okay? Does that make sense to everybody? Go.
Is that nonce randomly created, or is there a pattern of some sort?
Yeah, so when you download sort of the Bitcoin software, this is all handled behind the scenes, right? You don't need to worry about it. But the nonce is just a constant that gets fed in, and there are some certain specifications that the nonce needs to fit, but it gets hashed together, and then you get a resulting hash. And that resulting hash, it needs to fulfill certain specifications, so we change the nonce because that's the only thing we can change, right? Okay, so again, if the Merkle root gets tampered with, then we know that this next block is not valid because it's not based off of a valid last block. Okay? No further questions? All right. So then we talk a little bit more about the nonce. So it's used to implement proof of work in Bitcoin and every other cryptocurrency that uses proof of work. These hash puzzles need to have these three properties, right? We need to be able to easily verify that somebody has completed that hash puzzle. We need to have the hash puzzle be computationally difficult because that is the reason we have this whole idea of one CPU, one vote, back to Satoshi Nakamoto. If you don't tie your vote to a resource, then what's stopping people from just generating lots and lots of public keys and just lots of addresses and voting for myself, right? People, I don't see a reaction to that. Does that make sense to everybody? Yeah, okay, solid. And then you see it's less than the target. So if it's less than the target, then we need to play with the nonce some more, and then so that we hit that target, and then everybody will be able to recognize that this is a valid block. Yes? Okay. So now we talk about what exactly mining means. So mining is like throwing darts at this target while I'm blindfolded, right? This is the idea of brute force. And we have equal likelihood of hitting any part of this target. People who throw faster hit this entire thing faster. They hit more times per second. And so miners look for a hash below that target. And they're going to look like just at the bottom there, that hash of everything. They want to be below some target. Okay. And that's what I mean by the leading number of zeros. Okay. Make sense? Can I get thumbs up when it does make sense? When I ask? All right, solid. Okay. And so we define difficulty to mean it's some representation of the expected number of computations required to find a block. And so as mentioned earlier, we have that 10-minute confirmation time with the difficulty adjusted every 2 weeks. So that information is just pretty standard to the Bitcoin blockchain, but it's unique to the Bitcoin blockchain. And so the way we talk about difficulty is then we adjust this need for, we adjust the amount of time it takes to mine a block. And so they calculate that by, they calculate this difficulty by this equation down here, and you can see the time to mine the previous 2016 blocks. That's what translates to 2 weeks. And so they look at the past 2 weeks of blocks, and from there they define the difficulty for the next 2 weeks. Okay, and make sense? Cool. All right. Okay, so we're going to do a quick demo. So I will also put out instructions if you want to play around with this, but this demo is just meant to sort of demonstrate everything synthesize everything you've learned. And so this GitHub repository was put together by one of my colleagues at Berkely, but okay. So I'm just starting up a local blockchain in this case. It's just an application that people have written called Block Shell. Who here has played with this? Okay, so I recommend everybody goes home and plays with this. And I have some instructions here for myself. So when we create the blockchain, everybody should know we have a genesis block, right? With the Bitcoin blockchain, our genesis block is what holds all of the Bitcoin that will ever be created. So some number of Bitcoin have been created, and when we have the block reward, that's what pays out from that original genesis block. Yes? Okay, so here, this is our genesis block. I just started the blockchain. I initiated my difficulty for the proof of work to be 3, and this is the hash of my genesis block. So I'm going to get info on this block. So all I've done here is I've typed in get block, and then I've given it the hash of our genesis block. That is the first one. And here you can see the data is that this block knows it's the genesis block, and this is the hash. And then the nonce is 0, because this is my first block, so we don't have a nonce, right? And there's no previous hash, because again, genesis block. So then I'm going to go on and create a transaction. Yeah, question?
What is it? Is that TX count, transaction count?
Yes, so that's the transaction count. You can imagine that to translate to the number of transactions in total that Bitcoin will one day, like how many Bitcoin one day. The transaction count for the Genesis block is a bit buggy. Don't mind that too much. Yeah, but for when we mine the next block, you will be able to see. So I'm going to create my first transaction. Does anybody have a suggestion for the sort of comment we can save in there?
Hello world.
Hello world. Okay. Never heard that one before. Okay, so .x hello world. You can see it's processing the transaction. Okay, and perhaps we'll do one more. Anybody else suggestion? Okay. Okay, so now I have two transactions. And so if I look at the mem pool, my transaction pool, I should be able to see that I have two transactions, right? It has a timestamp, it has all this metadata information about my transactions, and then I have 0 indexed transactions and my transaction data saved in there. Okay, any questions so far? Should be pretty straightforward. Okay, so then I'm going to mine my first block. Perhaps I will make one more transaction. Okay, so now I'm going to make my first block. It's quite straightforward, right? Mine blocks. And then which transactions shall I include? Suggestions? 1 and 3, okay. So I'm going to mine blocks and I'm going to include transactions 0 and 3. Oh, 1 and 3, right?
0 and 2.
0 and 2, okay. So 0 and 2. And so you see then I have mined my block and it has taken me 0.01 seconds. So the time that has elapsed between mining is dependent on, anybody has answered for that? What is it, the time it took to mine dependent on? Length of the chain. So it's not necessarily dependent on the length of the chain, it's more dependent on the number of transactions that I have to process in my block. And furthermore, it's dependent on the difficulty set. And so that difficulty is really like the important part here for defining how long it's going to take me to create my block. Remember, the difficulty translates to the amount of work, how difficult it is to find that nonce, how small that my target is, and how many brute force computations I have to do before I can mine a valid block that everyone is going to accept. Any other questions? Yeah.
What's the top?
This is a demo, so.
How hard could it get set?
That's a good question. I'm anticipating probably like arbitrarily high. We could play around with that and take a look. But for example, even if I made the difficulty 0 or 1, you should be able to see some sort of minor difference in how much time, because you see this is in milliseconds. Yeah. Okay. Any other questions? Okay. So then we continue with the demo. And so if I continue, we've mined my first block, right? So if I do all blocks, now I see that I have 2 blocks. And you see that here, I have some leading number of zeros, right? Okay. I should see that in my data, I have the 2 transactions, and then I have the hash of this block. I have my index, because this is block 1. I'm 0 indexed. And then I have the nonce, which is just some constant, remember. And then I have the previous hash, which is just my genesis block up here. Okay. And this is a summary of my blockchain. Transaction count is 2. Yes?
You referenced the leading zeros.
Uh-huh.
I've heard that a whole bunch of times.
Okay, let's clarify that then.
Is that specific? Must it have leading zeros, or is that just one of many options?
Right, so if you go back to the definition of the puzzle I gave, we are trying to hit some target. And so the leading zeros translates to how small your number is going to be. And you're aiming to find a number that's going to be smaller than some target. And so that translates to being able to generate a hash that has some leading number of zeros, also known as you can find a number that's small enough to be smaller than the target.
So the target
Yes.
keeps changing every few weeks?
Yeah, so the target will change. The target will change every 2 weeks because that's how the difficulty changes, right? We must reset the difficulty every 2 weeks.
Who's changing the target?
This is already built into the protocol, right? Because you don't, first of all, you don't want a centralized entity doing that. And second of all, you want it to reset every 2 weeks, precisely because things like ASIC miners come out. And then, well, everybody who is mining Bitcoin and doesn't have an ASIC miner is in trouble. So, okay, does this make sense to everybody? And a thumbs up. Okay. So I want to talk about signatures and addresses because the ability to sign off on a transaction is that's your digital signature, that process. I'm sure everybody here knows what a public key, private key pairing and what that is, but the context in which we want to talk about them in the Bitcoin context and how that fits into how we build a transaction is important. So we'll go over it again. So just a refresher, Alice is going to use ECDSA, which we'll go over in a little bit. But she uses ECDSA, just trust the crypto magic, to generate private and public keys. So she has her private key and public key. She's going to send over her public key because everybody has access to her public key. It's like an email address. So Bob can see her public key. Alice will sign her message, and so she has this little signature, and it's going to show up over with Bob. Okay, so Bob has Alice's message, he has her public key, and he has her signature that she signed off on. And so Bob can easily verify whether or not Alice signed this signature using the public key that he has from Alice. This should be a refresher for everybody. Thumbs up, temperature check. Cool. Okay. And so Bob, this is important, right? Bob should not be easily able to guess Alice's private key. And if Bob can easily guess, well, then this is problematic and we don't have Bitcoin anymore. We don't even have RSA, but this should make sense. So then if we have Eve in here, and Eve has her private key, and she's trying to intercept or pass her message off as Alice's, then Bob is going to see Alice's public key and Eve's signature, and it's not going to fit, right? So he's going to reject. It's a bad message signed by the wrong person. Okay, no questions? Moving on. All right, so let's talk about elliptic curve cryptography then. So the reason it's important here is because Bitcoin uses ECDSA to produce those public and private keys. So who here is a mathematician and knows what ECDSA is? Oh, good, okay. No one will call me out. But so this elliptic curve here is just a mathematical function, right? And so a broad overview, don't want to bore anybody. So Bitcoin's elliptic curve, the exact one is this function right there. And if you're interested and you have a math background, go and look it up. And then you can come back and teach me. It's hard. But for cryptographic purposes, we have a finite field and we draw this elliptic curve. And then we're going to do this multiplication. And so it's just we show that our elliptic curve turns out to be a trapdoor function, and we do this chord-tangent process of multiplication. And essentially what that boils down to is this discrete logarithm problem. So we have our private key, we have our public key, we're going to multiply that some number of times, and then we hash that twice. And so that becomes our address. The reason we hash it twice, we hash it with SHA-256 because for security, and we hash it with RIPE-MD for brevity. So because the SHA-256 one is too long, we want to make our public key address a little bit shorter, so we hash it again. And so this boils down to, we can reduce this problem to the discrete logarithm problem. And this turns out to be quite difficult to solve, computationally infeasible, and so it's not quite impossible to solve, but it's computationally infeasible, and that's as good as. And so this is sort of like an introduction to the cryptography that Bitcoin addresses, public key pairings rely on. And this is why you can't really retrieve the public key, private key from the private key from the public key. Okay. Any questions? Yes, go.
So there's been this talk of double hash.
Yes.
So here I see it's RIPE MD 160 and then SHA-256. Right?
Yes.
Then on the mining side, it's SHA-256 off the actual message. So are these two different sections?
So this is just how we generate our address.
Okay.
Yes. And we apply SHA-256 first for security, and then RIPE-MD, yes.
Which is different than the other one where on the mining side.
Yeah, so that's a bit different. Yeah. They use all of these multiple times, but just in different orders.
It's all the context.
Yes.
Different. Okay.
Okay. Any other questions? That's good. Yeah.
RIPE-MD, what is that?
RIPE-MD is another hash function, and it just shortens the SHA-256 one. Yeah. Okay. Any other questions? So yeah, this is just again what we were saying. Our public key hash will then consist of this double hash, and SHA-256 is used a lot in Bitcoin scripts, as you know, and in mining. RIPE-MD, it produces just a shorter hash, and so this is all so that we can make sure that we have this tamper-evident. So you see there the base 58 check encode. This is just a way for you to be able to, like, we append something at the end so that you can very easily check whether or not you've typed in your entire public key hash correctly. So if anybody here uses, for example, Coinbase or some other Bitcoin wallet, often they will append some sort of checksum at the end. So it's like just 3 letters, and it summarizes essentially all of your hash. And so if you typed in like one letter incorrectly, that checksum should change, and you should use that to make sure that you've typed it in correctly, because otherwise you might have some headaches. Any questions about this? Cool. All right, let's keep going. Right, so this is just some more information about how we construct that Bitcoin address. These are all, it has a base 58 alphabet. We use all of those 58 characters, and then we omit the 0 and O and 1 and I, because those are confusing. And then we have this prefix and that checksum. That is what I was speaking about earlier. Okay, any questions? Yes?
So who needs to be concerned with the actual hashes happening for address generation? Because these are generated by the Bitcoin network, right?
Yep, so it's actually
Other than
very...
them, who else needs to be concerned with this?
Well, anybody who is participating on the network should be concerned about how exactly you're constructing the Bitcoin address, but it's very, very simple to generate an address.
Right, so if I'm working on the wallet, hardware wallet, should I be worried about this one? Should I be doing the reverse process of this?
Perhaps not the reverse process, but...
Or on the decode side, right?
On the decode side? So you're talking about like some user interface stuff, I guess.
Or my question was more
Yes.
because the mining side, which employs the SHA-256, the double hash.
Yes.
So that does not have to worry about it.
No.
Because that's purely on that side, right, reward, etc. So if these are generated for the address, then I'm just trying to see who's the receiver side who needs to validate that this was the right address. So that was my intent of my question.
So that is all handled in the Bitcoin script of how we construct a transaction. And so we'll get into that in a little bit. But this is just how I generate a public key. And there's lots and lots of software. It's very easy to just like search generate public key for Bitcoin, and there are like a lot of websites out there that will just very easily generate. There's even a website out there that, because there are so many public keys and private key pairings, there's a website that you can go to, and just keep refreshing the page. It'll generate public keys and private keys, and then it looks it up in the Bitcoin blockchain. It'll look up how much money currently exists in that account, and you can just keep refreshing the page. But because there are so many public key, private key pairings, it's very unlikely that you'll have a pairing show up that actually has money in the account. But if you do see one that does have like some amount listed, well, you'd have the private key and the public key, and you'd have access to the account. But the point of the exercise is just to say, like, there's so many public key, private key pairings that people can do things like this. So that wasn't as relevant, but it's just a fun aside. Okay, any other questions? Okay. Did I answer your question? Continue then.
There's one portion that's not answered.
Okay.
So let's say if I'm actually trying to come up with some solutions for the wallet.
Sure.
Maybe a better hardware wallet, right?
Okay.
Key-based, whatever that be. Would I have to be concerned with this address validation and the right MD160 and SHA-256?
This is on the generation side.
This is on the
And
generation
so,
side. So on the wallet side, I'm assuming there would be some kind of validation of these addresses. So, or more, the direct question is, what would be involved in the wallet in terms of the hardware?
right, so as a wallet, the wallet is just simply providing a service for you to keep your public key, like your address and then your private key. And if you have that, then you can log into your wallet, and the wallet provides like an easier interface, depending on which wallet you go with, provides an easier interface for people to interact with the Bitcoin blockchain. So depending on, for example, with Coinbase, if I forget my login, it's not the end of the world, right? Coinbase has like 2-step factor authentication, so I can find ways to retrieve my public key address. And people use wallets precisely because they have that extra layer of security. So as a wallet like manager, you might want to worry about like the verification, but this isn't your biggest problem. It's more convincing the people that you are servicing that you are securely holding all of their private key and public key pairings, and that you're not collecting information on them as they proceed with their transactions. Okay, does that make a little bit more sense? We can talk further about this. Right, okay, so to go on. So let's talk a little bit about Bitcoin script. Okay, so reminders, Bitcoin uses that UTXO model. This looks familiar to everybody? Yes? Do I need to talk about okay, we'll talk about it a little bit. So UTXO model is unspent transactions, exchange account, exchange output, something like that. So transactions will map inputs to outputs, and I just need to break a piggy bank or break some sort of transaction and then send it to somebody else and send whatever is remaining back to myself. Yes? Okay. And so spending Bitcoin is equivalent to just redeeming previous transaction outputs. Okay? And so this becomes important because that has to do with how we have to build our Bitcoin. That's how we build our Bitcoin transaction. We need to make sure that the specified recipient is the only person who can unlock those or redeem those funds. And so that's what we're going to talk about. In this case, we have that transaction, we have our index of the previous input, and then it's going to be into the script signature. So this is what we're building, right? We need to build something, use the scripting language to create something that's going to tell whoever receives this block that Alice is trying to break up her previous transaction, or Alice is trying to deliver this previous transaction to somebody else because she's spending this previous transaction.
X amount of that previous block.
So she's referencing a specific transaction in the previous block. So let's say if we go back to the mental image of what our block consists of, the MERKLE root, and then the MERKLE root is sort of our summary of all of the transactions. She's referencing one single transaction in there, and then like inside that transaction, perhaps she's breaking it up or she's deciding whatever she wants to do with it. And that's going to be what we're going to talk about, how exactly she goes about summarizing all of that and putting it into a script.
So it just takes a portion of that
Yeah, so she's going to reference that transaction. I'm sorry?
as she designates.
So she's going to designate part of it, but if she even touches that previous transaction, because of the way we do this, because it's summarized in this previous transaction hash, if she breaks it, she needs to send any of the remaining Bitcoin. Let's say she had 10 Bitcoin in this first transaction hash, right? And she only wants to spend 5 of it on buying a pair of sunglasses from Bob. It's an expensive pair of sunglasses. She needs to be able to send the remaining 5 back to herself, because otherwise that 5 just gets lost, right? Make sense? Okay. And so in this manner, we need to have some way of summarizing what exactly Alice would like to do with all of her Bitcoin that exists in this given transaction. Does that make sense? Very good.
That's the whole question.
Okay, solid. Any other questions?
Right, so that part, the $5 that she spent on the, so how does she get back the remaining 5? Does she create the transaction with 5 coming back to her, because it was a transaction with $10, with 10 Bitcoins coming in, right?
So that's what we're going to get into, right? She has to have some way of summarizing everything she wants to do with her Bitcoin in that given transaction. Because she's breaking open a piggy bank, well, there's no piggy bank to put it back into, right? So now she must find another piggy bank to put it into.
Okay, and all of that needs to be described in this.
Exactly, right. So we're running out of time. We must get to the actual thing I keep promising.
Ask questions.
No, but this is good. Hopefully this answers like more than it would just me throwing information at you. So this is the output, and here we can say, we describe like the value, the output amount, right? How much Bitcoin she's trying to access, and then down here you see the script pub key. So we will describe this a little bit more, and we'll get into some more detail, but you see just opt up, op hash, and op equal verify, and op check sig. And so these are just operations. She's building sort of like, so all of this is concatenated together, and we're building this in order to provide instructions to whoever is trying to validate her transaction. And so if we continue, I'm assuming no questions because we did talk about that for a while. Script pub key here, so opt up, op hash, and again, op equal verify, op check sig. This is an output script. And so output addresses are contained in scripts. And so our inputs and outputs through scripting, this is what we call Bitcoin script. At the very end here in the output, we have incorporated something that is going to tell anybody who is verifying Alice's transaction how exactly and what exactly she's planning to do with that transaction. Okay, does this make sense? Okay, so we're going to go through just briefly what exactly each of those is. So previously, I think it was mentioned that Bitcoin script is sort of a push-down automata. And so what's really meant with that is we execute it like this. So script pub key, opt up, op hash, downwards. And so we have our new transaction input up there, and then down here we have our previous transaction output. And we're going to just execute each of those. And so op duplicate just duplicates the op code because we're going to execute some of them. Op hash just hashes. Op equal verify is going to check things like that the script sig that she provided is equal to the script sig that is required. And then op check signature is going to check that signature again, verify whether or not the amount that she wants to spend is equal to the amount that she has ready to spend. Does this make sense? It's just essentially like a bunch of operations concatenated together that will describe what exactly Alice wants to do with her code. Yeah, okay. And so P2PKH and P2SH, some very similar acronyms there, but so in Bitcoin, senders specify a locking script and recipients provide an unlocking script. And so if we go back to this, well, the locking script and the unlocking script are the first and the second. And so a locking script is the idea that when I send Bitcoin to, if Alice sends Bitcoin to Bob, she needs to provide a locking script so that nobody but Bob can access that Bitcoin. And that's what we mean by locking script. And then when we say unlocking script, well, that's what Bob must provide, right? He must provide some way to unlock his own Bitcoin. That should be pretty straightforward, but it's the general structure of how exactly we construct that operation that describes what we do with a given transaction. Does this make sense? Yes? Okay, cool. And so this is where, if anybody has talked about multi-signatures, this is sort of where we fit in. We get into the idea of having multiple people. Like, for example, you can't have, let's say you're running a shop, and I'm running my shop, and we have 3 partners. Well, if a customer comes to me, I cannot really be like, hi, customer, you need to provide this very complicated op signature, opt-up, op-hash, whatever. You need to build that so that in such a way that 3 of us can spend. That's more complicated for the customer, and so that's why we have the vendor or the person receiving provide this complicated output script that allows them to spend using signatures. And this is sort of like where you start putting in this idea of multi-signatures, this idea of like extended abilities. That's how Bitcoin script becomes relevant inside this output section. Are there any questions about this? Okay, sounds good. So let's talk a little bit about scalability. I know this was covered in the previous section. And just really quickly, in case anybody has any questions. So we talked about the trilemma of security, decentralization, and scalability. We talked about this, and I'm going to go on. So Ghost is the idea of, so if we want to decrease block creation time, I believe this was brought up earlier, how this is not necessarily a great idea, but Ghost is a relevant protocol just because it was implemented in Ethereum. And so in this way, we increase the speed of blocks by decreasing the difficulty of proof of work and the weighted proof of work blockchain. And so this is potentially a very high level understanding of why exactly we can do this, but it's a name to go look up because Ethereum did go on to incorporate this. And the reason for that is essentially a broad overview is that we can include blocks that were orphaned. And so people who mined blocks, let's say 3 people have mined a block at the same time, and only one of them can win. Well, then our other blocks are sort of orphaned, and people have like very little incentive to continue mining if they have, if their blocks are consistently becoming orphaned. And so for this reason, we want to incorporate them, provide them some small block reward for people who have perhaps not been included onto the blockchain. And so this is sort of an interesting avenue of ideas that people have pursued. And this is one way that they've approached the problem of being able to increase the speed of blocks. Again, this is a very high level overview. I'm not sure how much background you guys have for this, but it's an interesting idea to go look up. Okay, and so this has increased the Ethereum average block time. Okay, and then increasing block size. I believe you guys talked about potentially the problems with just increasing how big the block is. This is the main thing behind, this is what has changed between Bitcoin Gold, Bitcoin Gold, Bitcoin Cash, and the regular Bitcoin. One of them is now 8 megabytes, and it's just much bigger than like our regular Bitcoin. And this is all very controversial, right? A lot of people disagree, which is why we have all of these different cryptocurrencies that have branched off. But these are some of the cons of why exactly increasing the block size might be bad. Again, the slides I'll make available, but potentially I think people had some questions about segregated witness. So just really quickly, the signature that is there, you only need the signature to verify the first time. And then down here you can see we have the Merkle tree of a transaction, and we have a witness that is just building a Merkle tree of all of the signatures. And so if we have some way to keep track of people who have we've verified a transaction in the past, and we're going to trust that any transactions that come in the future any transactions that have already passed were verified, because that's sort of the premise of the blockchain. And so for that reason, we can sort of abstract away the signatures. Does that, that might not sit well with people. Does anybody have any questions about what segregated witness is exactly? No questions? Did I throw too much information?
Yeah, can you word it again?
Yeah, sure. So for segregated witness, the main idea is that there's unnecessary information in my transaction. So I can sort of remove some of the extra information that is perhaps only necessary once or twice, that we don't need to keep in the overall size of my blockchain. And so I'm going to remove some information about the signature. And then the question becomes, well, how am I going to make sure that my transaction is valid now? Because the script sig is very important. And so the the solution to that is we verify it the first time, and then we trust that if it's ended up in the blockchain, well, we trust that it's been verified in the past, and we can build off of that. And so it's listed as a pros and cons list, right? There's a potential to lose the history of these signatures, but it is a way to fit more transactions into one block. And yeah, there are pros and cons, and people disagree, but this is sort of the broad idea of what SegWit is able to do. Okay, any other questions? Okay. So some ideas just broadly, horizontal scaling. This idea of sharding is the idea that you don't need to require every miner to be working on every single block. And essentially you can create parallel blockchains. And so they work together in order to create blocks. Okay, this is just defining some terms that you might hear in the space. Sidechains is the idea that you perhaps can't speed up the Bitcoin blockchain, but you can take your transactions off chain, execute a whole bunch, and then bring it back and settle on the original blockchain. Okay, yeah, so this is just a graphic, and then this is a summary of Bitcoin, Bitcoin Hash, and Bitcoin Gold. So you see that Bitcoin Cash has increased the block size, and so their aim was to have a faster network and smaller fees, precisely because they were able to fit more transactions into a given block. Bitcoin Cash was hedging a bet that regular Bitcoin would not go on to adopt things like Lightning Network, like atomic swaps, and that Bitcoin would eventually become less competitive when compared to Bitcoin Cash, precisely because of those transaction fees and that scalability problem. However, Bitcoin has gone on to adopt Lightning Network, as was spoken. I think they pushed their most recent release in April. And so they're doing pretty well, and people have stayed with the standard Bitcoin. And so Bitcoin Cash is still trying to compete there. And Bitcoin Gold uses a different proof of work algorithm, EcoHash, and their idea was to re-decentralize mining. So going back to the idea of one CPU, one vote, Bitcoin was based on that original idea, but as I think Shiva mentioned earlier, Bitcoin has become quite centralized. A lot of these mining pools, mining conglomerates, find it easy to just throw capital in there, and they buy a lot of ASICs. They have cheap electricity, and they are able to churn out Bitcoins. And in that way, it's become quite centralized. Okay. Any questions quickly on comparisons? Yes? Oh, never mind. Okay. Oh, yes. And so this is just a comparison between Bitcoin, Ethereum, Ripple, and Zcash. And so Bitcoin, they use different consensus algorithms. Ethereum has moved towards something called Casper, which perhaps you guys didn't talk about proof of stake yet, but it's another consensus algorithm that finds another way to tie. So in Bitcoin, the proof of work, the resources that we use are electricity, because we brute force some nonce. Remember, we have a target we need to hit. We just brute force that math computation. In Ethereum, we use, they're moving towards an idea that you can not use such electricity, so much electricity, and you can find another resource to tie your proofs and your evidence of work to. And so they're moving towards a more hybrid system that uses less electricity, and that's called Casper. Might also be interesting to read about. Ripple has their own, and Zcash also has their own. But these are all sort of interesting things to talk about, interesting things to look at. And understanding the differences between these different cryptocurrencies is quite useful in understanding why exactly people have made certain choices in designing their cryptocurrencies. Okay, so I think we can skip past Lightning Network. Does anybody have any broad questions for me? Otherwise, we can talk a little bit about ZK snarks. Oh, good question. I don't know. I'm sorry. I can find out and then let you know. But that's a good question. Did you say 4 million?
Yeah, roughly 4 million, it would take more than a century to.
It's a long time, but it is finite.
Last Bitcoin will take 35 years.
Yeah, but people are potentially worried about what happens after we've mined all the Bitcoin. The idea that is sort of propagated is that the network will continue based on transaction fees and such, and the community will live on, and that's the idea. So another interesting thing I just want to end on, so Monero is an interesting cryptocurrency to look at. I think it was mentioned earlier, it's a privacy-centric, and the reason they can do that is back to the idea of like multi-signatures and ring signatures. So there are all sorts of cryptographic tricks to make it, so Monero is more anonymous than your average Bitcoin, and it might be interesting to, if you're interested, you can come talk to me after about why exactly they are able to achieve more anonymity. And then, do we have time to talk about ZK snarks? Who's in charge of telling me that? Is it okay? Okay, cool. So let's talk briefly about ZK snarks. So they stand for zero knowledge, succinct, non-interactive, et cetera, et cetera. And what's really useful in understanding that perhaps is, imagine there's a man who's blind, he's colorblind, and he has two pens, one that's red and one is blue, and he hides them both behind his back, and he's interacting with another person who claims to be not colorblind. And he'd like to be able to tell whether or not this other person is lying to him about being not colorblind. So he shows them the two colored pens. He hides them behind his back, and he has the option whether to switch them or not switch them, and then he'll show them again. And if that guy will be able to tell him, oh, you changed the pens, or no, you didn't. And if he does that enough time, probabilistically, he is able to tell, like, you are lying, or you are not colorblind, and you can in fact tell me with a high probability when I've actually switched them. And so that's the idea behind being able to, with zero knowledge about your transaction, like you don't have that much information about this other person, but you're still able to gain some information about them. And so if we translate that idea over to being able to build proofs, the idea is that I can obfuscate away this information about input-output addresses and their values. And I can hide all of that and still be able to generate a proof on whether or not a transaction is valid. And so that should be, given everything you've learned today, hopefully that's sort of an amazing thought, how exactly you can do that. And so that's an active field of research, but Zcash is one of the cryptocurrencies that makes use of that sort of idea, that we can even further obfuscate information about people, and that's very valuable to people who value anonymity and stuff like that. ZK snarks are not only useful in the blockchain context, it's this field of ZK snarks and homomorphic encryption and whatnot is quite useful just across all industries, but in this particular context, Zcash has some good good documentation on what exactly it means. Are there any questions about the broad topic? I don't know that I'll be able to get too much more into this. No? ZK snarks are cool, you should look them up. Yeah, okay. So if we talk briefly about it, this input and output, the idea is that I can hide like who sent the transaction and who is receiving the transaction. And more than that, I can also hide, like I can lock the output details of each transaction. And that should be quite interesting on how exactly we can do that, but we must trust it to crypto magic. Yeah, but the difference between Bitcoin on the top and Zcash on the bottom. Are there any questions about this given graphic?
If you can tell most of people how Zcash can achieve some of it. For example, if I have public key on Bitcoin, people can follow on the transaction.
Yes.
So how Zcash will do that?
Yeah. Well, so it obfuscates who exactly is creating this input and who it's being sent to. And so the same way in Bitcoin that you can go and look up some given public key. Let's say I have your email address. I can go and look in the Bitcoin blockchain because it's completely transparent. I can look up all the transactions you've made. In this case, I wouldn't be able to because you see this is obfuscated, and so I have nothing to look up. And so, yeah.
How does it know that you have the cash to spend?
What an excellent question. So you see that Zcash is adding another layer on top of this original like Bitcoin idea. And so we have this zero knowledge security layer that is based on the Bitcoin code base, but it enables transparent transactions in such a way that we have the signature of the sender, and this is sort of a confusing graphic, really, but if we have zero knowledge, we're still able to generate a proof of validity for a given transaction, and that's what the entire like ZK Snarks idea sort of hinges on. This idea that we're able to generate a proof of validity even without understanding, even without having like the explicit public keys. Okay, that might not be a very satisfying answer. You can come talk to me after. Okay, and then this is, again, just the idea behind homomorphic hiding. But perhaps with our remaining time, it might be more useful to talk about the idea behind Monero and ring signatures, which is also sort of like an interesting field right now. So in ring signatures, we have these two properties in Monero. We have untraceability and unlinkability. And this comes back to like the benefits of improving upon Bitcoin's anonymity. And so the reason we can do this is imagine we have Alice, Bob, Carol, and Dave, and they all have public key, private keys, right? And so when we get a transaction, we simply know that one of these three has signed off on it. So the bigger our group of N is at the beginning, the more difficult it is to tie a specific transaction to one person, because it could be any of Alice, Bob, or Carol. And so this idea of having multiple people sign together in this ring, then in such a way you can't tell which one of the ring was the person who actually sent the transaction, because you're signing with everybody's. Does that make sense, this idea? And so in this way, even given some sort of public key, we can take that to the transparent blockchain and still not be able to retrieve who exactly was the public key address that sent a given transaction. Okay, and this is perhaps a more processable idea. Okay, any other questions? Okay, and so in this way we have a one-time, and then further, Monero, more than that, also does this idea of like having a one-time address. So it'll generate an address and then obfuscate Bob's transaction by adding in some extra steps. So you'll have a one-time address that sends something to Bob, and then you won't be able to see Bob's address because it'll be hidden in sort of a list of different transactions. People look confused. Yes?
Is this a user setup ring, or is it generated?
Yeah, so this is completely handled by the Monero backend, and that's why this is perhaps like quite impressive. But specifically in Monero, you can sort of toggle the level of anonymity you want, because the higher the anonymity, the more they can charge. So you can toggle the transaction fees and anonymity accordingly. Yeah, so not everybody wants to completely hide to this level, but if you would like to, they can obfuscate your one-time address behind more transactions and such. Okay, and so this hopefully gives you sort of a basic idea of how exactly we can play around with the properties that we know already and provide even more anonymity than was already provided. Okay, so a soft fork is generally more valuable just because in this manner we can, people are less adverse to the idea of a soft fork because it's backwards compatible, which means that even if you don't agree with the changes that were made, you're still going to be able to operate on the blockchain network. So for example, with SegWit, if we go back to that slide, yes, so back to this slide. With SegWit, even if this was a soft fork, and that's perhaps the reason why it was more amenable to people. The way this was a soft fork and the way this was implemented consisted of if you built a block that was slightly smaller, that contained more transactions, that you had taken out some the script signature and you'd taken out all this information, well, the old nodes that hadn't ratified to this new change would look at your block and would be like, whoever sent this block is crazy because they haven't included a script signature. Anybody can redeem it, but it's not my problem. It's still a valid block, so I'm going to pass it on. And in this manner, it still includes the old nodes that haven't verified or haven't ratified to this new protocol decision. And because they've built out the infrastructure in such a way that allows old nodes to still participate, you call it a soft fork. It's more amenable to people. If you have a hard fork, then it's not backwards compatible, which means that all of the old nodes that don't adopt this new change you're implementing can no longer participate now. And so that means that things like Bitcoin Cash, Bitcoin Gold, the reason they've gone off and forked off is because they've made enough changes that they are no longer backwards compatible. People have to choose between one protocol or the other, and they're branching off into two different chains. Does that make sense to everybody? Okay.
So that your Bitcoin is available on the one you want.
Okay, so if you were around for when Bitcoin Cash became its own hard fork and split, your Bitcoin exists on both chains. And so essentially your money has doubled, right? Because now I have my original Bitcoin, but because they were both coming from the same branch and then we broke off into two, well, now I have Bitcoin, but I have it in two places and I can spend it in two places. And so does that answer your question?
Yes. Yeah, so if it's a hard fork, it has to replicate both places.
Right, because you're still building off the same original blockchain.
So it could devalue both of them, it could devalue one of them. It's really up to the market as to what's going to happen.
Right, so if you have a fork that's come off and you've made enough changes to the protocol that some people have ratified to this other fork, like a miner makes its own individual decision. Perhaps that's ideological, perhaps it's economically incentivized, but depending on which sort of branch of the blockchain you end up on, well, now you're verifying all of the transactions for that given blockchain. So you're verifying all of those transactions according to a new protocol, and you're verifying all the transactions. You've agreed to hold all of the blocks that come your way to a new standard that's different from all of the other blocks. Yeah. Any other questions?
So I heard you say the money doubles.
Yeah. So if you had money in Bitcoin Cash and Bitcoin Gold, Bitcoin BTC and Bitcoin Cash, BCH, well, because they come from the same blockchain, and then they've forked and now have become two blockchains. Well, if I had money originally, well, the money doesn't disappear, right? They're still in both.
It's duplicated, and so you're saying, so now it's twice the spending power?
Not necessarily, right? Because Bitcoin Cash specifically is valued lower. And so it's valued lower, so I do have the technically same Bitcoin. I still have BTC here, but because BCH has gone off and done its own thing, I still have BCH. My money still exists on that blockchain.
But then if you allow the course of time, and then that Bitcoin Cash could also have appreciated it.
Yeah, potentially.
With one Bitcoin, due to the fork, it ended up with
Potentially,
on the main,
yes.
And then whatever appreciation on the other.
Yeah, potentially. The point is that now I have whatever, we call it magic internet money, right? You have this Bitcoin and it's in two places. Perhaps you call it whatever, but it exists, its data in the blockchain. Your database has split, but the database originated from the same place. And given the properties that we've talked about, it's immutable. Your money can't disappear.
How can we force more forks then?
So the question becomes, you don't necessarily want to force more forks, right? Because the more forks you have, well, the more split off and splintered the community. And that's not necessarily good for your appreciation value or even really the development of blockchain. Yes, question?
More than 15 hard forks last year.
Yeah.
Three of them successful.
Second question was lightning.
I'm sorry, one more time.
The lightning update that's coming.
Yeah. Just explain that more. Okay, so first question I think was about the different cryptocurrencies and how that's affecting industry. So I think one thing that people like to say is cryptocurrencies are perhaps just currently the killer application for blockchain because this is what we hear about on the news, and it's not the only application for blockchain. You don't need a token for everything blockchain. And so that I think is something that is not said enough, so I'm going to say it. But industry-wide, I think, and this is my own personal opinion, I feel like blockchain is going to be integrated into industry in ways that are perhaps not as flashy as using a token. People aren't going to interact directly with the blockchain. In like 30 years, perhaps, it's going to be integrated in such a way that, like, if I go to the doctor, perhaps the doctor talks to, and this is branching off because healthcare industry doesn't always adopt technology like this, but if the healthcare provider talks to my insurance company and then I like only interface with one very small part of that, potentially that runs on the blockchain, and all healthcare records are now like on the blockchain somehow. That in that way, perhaps I will interact with the blockchain in 30 years, but I might not necessarily be trading Bitcoin. I might not go to a coffee shop and be able to spend some cryptocurrency, and I think that's quite likely, just because of the way cryptocurrencies are right now and the SEC stance on cryptocurrencies and tokens and classifying a lot of them as securities. And so it falls under regulations, and we do have to coexist with what exists. So. And so for the second question, the Lightning Network, we can talk a little bit further about that. I think I had some slides, yes. So the Lightning Network is this idea that we can have I think this was talked about earlier, but I'll just reiterate. So if Alice and Bob send a lot of transactions, sending them on the blockchain is very expensive. As we saw previously, it can go up to as much as $50 per transaction, and unless you're spending millions of dollars, that's not super sustainable. And so one way to get around this problem, some people call it cheating. I think it's interesting. Alice and Bob open a private balance sheet off on the side, and it's like a tab. They say, hey, like, let's just Venmo each other all of them, like transactions that we're going to do, all of the smaller transactions that we're going to do, we're just going to handle on the side over here. And then in maybe a month's time, we'll just take the tallies and we'll resolve that on the blockchain. And in that way, well, we've done all the transactions we wanted to, and we haven't had to pay all of the transaction fees. So that's the main idea behind Lightning Network. It doesn't seem perhaps super revolutionary, but it works, and it's meant to increase the amount of transactions that can be handled. It's gotten sort of cut around the problem of transactions per second, and it's not the only solution out there, but this is one thing that a lot of people were very excited for and might be worth taking another look at or continuing to follow. I did mention that they pushed an update on this in April, so now they have some code for you to play around with and look at. Yeah, I would recommend that. Are there any other questions I can answer? How are we doing on time again? Sorry, 1 second. Nobody is here. 10 minutes. Very good. Okay, continue.
So does this Lightning Network require, because it's an offshoot from the Bitcoin, right? Or is it Ethereum?
I'm sorry, Lightning Network.
Is the Lightning Network attached to the Bitcoin?
Yes, so it's a layer built on top of Bitcoin.
On Bitcoin, right?
Yeah.
Yes. So there is hardware for the Bitcoin network. Now, does the Lightning need a different type of hardware, like mining hardware, etc.?
Yeah, so the benefit of Lightning Network is that you shouldn't need any other extra like hardware.
At least the same hardware should suffice.
Exactly, because it's just a layer on top of it.
It's a layer.
Yeah. Okay. Any other questions? No other questions? Okay. Yeah. Okay. Keep going.
So given 2,000 cryptocurrencies, some of them are real currencies, some of them are tokens.
Yeah.
So for somebody who's looking at to actually contribute or participate in the hardware, right? What's the right approach, or what's the future for such that, because if the ASICs are already being hogged by 10 major organizations, then what is left for the other people to participate? So just some thoughts, or based on the direction that is.
Yeah. So a lot of this is actually software, but I think potentially a lot of use cases will require different amounts of hardware. So a lot of people like to talk about like supply chain use cases. So supply chain is one of the ones that like potentially you might use a blockchain for, because if you can find a way to tie, like a real life like water bottle, find a way to tokenize this, put it on the blockchain, and have a unique way to match this water bottle to a unique ID on the blockchain, then you can track this water bottle as it comes from China and then travels through each supply chain point. And that's perhaps one use case that people have spoken about that blockchain might be useful for. And I think there's a large potential there, and this is maybe not what you were talking about, but hardware in in branching how we interface with the blockchain. There are a lot of people, I think, in IoT right now trying to figure out how exactly we're going to be able to tie like a given object to something that's like a physical object tied to something on the blockchain is rather a difficult problem to solve. And I think a lot of like hardware people's interest in this is gone through IoT. But that is perhaps not what you were asking. You're asking about mining hardware, right?
Right, so
Yes.
mining hardware, that's already taken away by the
Yeah.
heavyweights. Right now, I just came across one case where for IoT, being able to provide cryptography with an 8-bit key, because it's so lightweight IoT sensor that you can't have a 256-bit key. So a 8-bit cryptographic algorithm, so that's an opportunity for people who provide IP. So
Exactly.
I think that it's called a GCT, Global GTC, right?
Yeah.
And so that was one example how somebody who specialized in algorithms participate coming up with that IP. So I'm just looking for
Other ways.
what are the newer opportunities or the problems that the networks are waiting to be solved. Right?
I
Because
see.
we did see, as you mentioned, most of them are on the software layer, how
Yeah.
to improve the transaction times. But any other insights on problems waiting to be
Yeah.
solved?
I will think further about this. I don't have an answer off the top of my head, unfortunately. Maybe one of the other speakers has an answer, better answer in terms of the potential for hardware for IoT and then also outside of IoT. But I will talk to you after because that's something I'd like to think about some more. Yeah, question. Yeah, so the SEC has unfortunately been rather quiet on this front, but they have come out with like a clarification of, I think it's the Howey test. It's the test for like whether or not something is considered security. And so certain tokens, depending on how exactly, this isn't about anonymity, and the reason I don't answer that is because, to my knowledge, there isn't a whole lot of documentation on that. If you look back at like what happened with Silk Road, people are able to find, like, generally able to do enough analysis to the point where they're able to tie a given Bitcoin public key to perhaps a real-world identity. And because that's like possible, it's been done in the past. We say Bitcoin is, first of all, pseudo-anonymous, and second of all, the SEC or like really any government entity hasn't really spent too much time on the idea of anonymity and the problems with that. More than that, it's been trying to like regulate it in terms of whether or not it's a security. And we do have KYC laws, so anything that the government can impose those KYC laws on, KYC stands for Know Your Customer, so you do need some amount of information about your customer. A lot of, like, for example, Coinbase has to like ask you for varying levels of personal identification before you're able to extract your money into USD, for instance. So if you're transacting upwards of $10,000, I think they ask for like a driver's license, something like that, just so that government doesn't get mad at them. So potentially we can take this discussion offline, and I'll end this workshop for everybody. You guys can continue talking. But if you have any further questions, definitely reach out. I'll make the slides available. But thank you guys so much.